All right, today we're going to pull back the curtain on a technology that shapes our world. I mean, quite literally. We're diving into CNC machining, the incredible high precision process that's behind so many things you use every single day. I mean, seriously, have you ever really looked at your phone or your laptop? How in the world do they get those perfect, smooth metal edges? Or think about a jet engine part or a surgical tool. How are those made with an accuracy that just seems impossible? Well, the answer to all of those is exactly the same. And here it is, CNC. It stands for Computer Numerical Control. And at its core, the idea is just brilliant. Instead of having a person manually guiding a cutting tool, we let a computer take over. And that gives us a level of control and, repeatability that's just, well, it's superhuman. Probably the best way to picture this in your head is to imagine a robotic sculptor. Now, this is what we call subtractive manufacturing. It's the opposite of something like 3D printing, which adds material layer by layer. CNC starts with a solid block of something, like aluminum or steel, and it just carves away everything that isn't the final part, leaving behind this perfectly formed object. Okay, so let's get to know this robotic sculpture a little better. To really understand how it all works, we first need to look at the basic anatomy of the machine itself. What are the key parts that are doing all the heavy lifting? So what's really interesting is how this sculpting actually happens. There are two main ways, milling and turning. And the key difference between them is super simple. It all comes down to what's spinning. In milling, the cutting tool spins and moves around a block that's held still, kind of like a dentist drill. But in turning, it's the total opposite. The material itself spins like crazy, while a stationary tool cuts into it. This is perfect for making anything round, like a table leg or a super precise metal shaft. And the two hero components in all of this are the spindle and the tool. The spindle is basically the powerful motor that does all the spinning. It either spins the cutting tool in a mill or it spins the entire workpiece in a machine called a lathe. And the tool? Well, that's the business end of the whole operation. It's the sharp, super hard piece that does the actual cutting. So we've got our robotic sculptor, but just like any artist, it needs instructions, right? It can't just look at a block of metal and know what to make. It needs a detailed recipe, a digital blueprint that's going to guide its every single move. So let's look at how this goes from just an idea to a physical part. It all starts in the digital world with a 3D model. Then that design gets translated into a special program, basically a set of code that the machine can understand. And finally, the machine just reads that code, line by line, and makes the physical cuts. This program, this code, it's literally the language of the machine, and it's an unbelievably detailed list of coordinates and commands. It tells the tool exactly where to go on the X, Y, and Z axes, how fast it should move, how fast it needs to spin, when to turn coolant on or off. I mean, absolutely everything is spelled out in this code. And out of all those instructions, two of the most critical ones are speed and feed rate. Speed is just how fast the spindle is spinning, and we measure that in RPMs, or revolutions per minute. And the feed rate is how quickly the tool travels across the material. Getting the balance between those two just right, well, that's the secret sauce for our perfect cut. Okay, so we've got the machine and we've got the code. Now it's time to move from the digital world of the computer to the physical world of the workshop, where the magic really starts to happen. Now, this is a super important point. You could have the most perfect, beautiful code in the entire world, but if your physical setup isn't right, the part is going to be a total failure. The machine has to know exactly where the raw material is, and that material needs to be held down with incredible force. And this is where something called a fixture comes in. A fixture is basically a specialized clamp. It's designed to do one thing: hold the workpiece in the exact same spot with a ton of force over and over and over again. This is what guarantees that every single part that comes out of that machine is a perfect copy of the one before it. So once that setup is dialed in, the whole process becomes this beautifully simple and repeatable cycle. An operator clamps in a block of raw material, they hit the big green start button to run the program, and once it's done, they take out the finished part. Then, they just do it all over again. And that right there shows you the true power of CNC. That simple, repeatable cycle is automation. It allows one machine, often with just one person watching over it, to churn out hundreds or even thousands of identical, perfect parts with almost no human intervention. This is what makes modern mass production possible. So we've covered the machine, the code, and the process. But all of this, it's all leading to one ultimate goal, one huge benefit that makes CNC so revolutionary, and that's the science of achieving near-perfect quality. If you take just one thing away today, let it be this principle right here. Every single aspect of CNC is about control. We control the tool's position, we control its speed, we control its feed rate. And because we can control every single variable with a computer, we can achieve an absolutely incredible level of precision. So just how precise are we talking about? A standard CNC machine can easily hold what's called a tolerance of plus or minus 0.005 of a millimeter. To put that into perspective for you, a single human hair is about 0.07 of a millimeter thick. So we are talking about accuracies that are more than 10 times smaller than a human hair. It's just an astounding level of precision. Now, in the world of engineering, this is all defined by specification and tolerance. The spec is the perfect, ideal size for a part, let's say exactly 10 millimeters. The tolerance is how much error is acceptable. How close to 10 millimeters do you have to be for the part to be considered good? And this is really where it all comes together. The inputs we control in the program, things like the spindle speed or the tool's feed rate, they have a direct, predictable effect on the final quality. If you want a better surface finish, you might increase the speed. Choosing the right tool makes sure the final shape is perfect. It's a clear cause and effect relationship. And the level of control goes even deeper than that. We're not just measuring the final shape. Advanced CNC processes can control things like the surface finish to get a mirror-like texture. They can even affect the material's internal microstructure and grain size, which actually determines how strong the part is. So in the end, that's the real magic of CNC. It is the ultimate bridge between the purely digital world of a computer design and the solid, tangible reality of a physical object, an object that's built with a degree of accuracy that was, not too long ago, completely unimaginable. And that really just leaves you with an exciting thought. With tools like 3D printing to add material and CNC to subtract it, we can now turn almost any digital idea into a real thing. So the only real question left is, with this amazing power of digital precision, what are we going to create next?